This is a very brief presentation of some of the functionalities provided by analogous chemoinformatics tools that have been developed by Nova Mechanics. This slide shows the overall steps required for the in silico prioritization of compounds for experimental testing via analogous platform. The workflow is initiated after defining a primary structure and identifying the positions of the possible substitutions on this structure. After the structure is converted to smiles, the user can select possible substitutions and the analogous de novo module automatically generates the new virtual derivatives. Among these, chemistry-driven derivatives are selected with the help of analogous ATMET tools, as well as the application of predictive models for specific priorities of interest. A pattern search coverage step can further narrow the selection of the most promising derivatives with the application of additional filters such as biological evaluation that is particularly useful for promiscuous compounds, the estimation of the acceptability, the price, and finally the commercial availability. For more information on our analogous tools, please visit our website www.novamechanics.com or contact us at info@novamechanics.com. Thank you for your attention.
Hello, we are Andy and Emil, and we are material chemists. And that means we try to link the synthesis with properties through the structure. And especially nanomaterials have our interest. In order to characterize the structure of nanomaterials, we use the pair distribution function, which represents a histogram of interatomic distances. So you can see an example here. In this work, we have used above 3,000 unique FCC structures and the corresponding PDFs, which we have given to conditional variational autoencoder, which task is to predict the chemical structure from the PDF.
Yeah, now to the validation of the model. So we've tried to reconstruct the structures and their corresponding PDFs, and we can see that they're very similar. So we have the ground truth and the reconstruction, and here we compare the PDFs, and we see a slight change in the atom positions, but otherwise it looks quite promising. Furthermore, we can visualize the latent space, and we see that the structures are clustered in correspondence with the number of atoms. We can also try to test the generative part of this model. So we have structure A and structure B, and then we interpolate between these two known structures and generating a lot of new structures. And it seems reasonable. And in the end, we would like to acknowledge the European Research Council and the US National Science Foundation for funding this project. Thank you.
Hi, my name is Nicola Bosch. I work at the European Bioinformatics Institute and more specifically in the Campbell Group. On the poster number 5, I present the result of a collaborative modeling project funded by the Bill and Melinda Gates Foundation. The outcome of this project is a web application to predict blood stage malaria inhibition. Malaria is a disease that affects hundreds of millions of people across the world, especially in sub-Saharan Africa and Southeast Asia. There are existing treatments, but they lack effectiveness due to drug resistance. Here we suggest using a machine learning model to identify new compounds with an anti-malarial property. Machine learning models usually see their performance improve with the number of data points in the training set, but such big datasets are generally private. Here we address this issue by sharing models instead of training sets. Our partners identify 11 in-house datasets of blood stage malaria inhibitions where compounds were classified as active or inactive against the Plasmodium falciparum strain. We provided a script using only open source tools, and it was used by each partner to train a naive-Bayes model per dataset. Only the model files were returned to us, and we investigated several consensus approaches to combine the models and obtain the best performance. At the end, we decided to use a meta-model that combines the features and weights of all the naive-Bayes models into a single big naive-Bayes model. With this meta-model, we developed a web application that we call MAPE for Malaria Inhibition Platform. MAPE is freely accessible, so anyone can submit a file containing compound smile for prediction. The model was experimentally validated by selecting 6,000 new compounds. The results have shown a significant enrichment in actives compared to a set of random compounds. More information on the machine learning protocol and the validation are available on the poster number 5. Thank you for your attention.
This work, which is titled Evolve, a genetic algorithm to predict protein traversability, we present a Python package that we have been developing in our lab that allows you to do rotamer optimization using a genetic algorithm. And the rotamers are optimized for optimal protein traversability, and here we developed a force field based fitness evaluation that is evaluated on the GPU. So this whole procedure is very fast. You can screen many rotamer combinations in a short time. And on the poster I present a benchmark of this tool on 3 data sets of multi-point and single-point mutants. So for the multi-point mutants, we see a very nice correlation to experimental values, and we use a variety of evaluation protocols that kind of honestly report the performance. And for the single mutants, we use 2 data sets. So one is a very large comprehensive data set that comprises all of these single site substitutions on the GB1 protein. And here our approach, in some categories, we are better than state-of-the-art, so better than, for example, Rosetta. But for some other mutation categories, our approach performs a bit worse. And here we discuss some of the kind of technical details where we still need to work on a bit more to improve the performance. But gratifyingly, on a small data set where all other tools that are state-of-the-art have shown no predictive power whatsoever, our tool can at least achieve statistically significant results. So that was a very nice first to see. And if you're interested in protein traversability, I invite you to check out our poster, which also contains some interactive features, so you can kind of explore the data set and explore some of the benchmark results interactively.
Hi, I'm Benny Fabian, and I'm going to talk about MORBERT, molecular representation learning with advanced language models and useful auxiliary tasks. This is a joint work with colleagues from Benevolent AI. MORBERT is a molecular representation learning method based on the popular language model BERT. In the case of traditional natural language processing, we would input a sequence of words, mask out some of these inputs, and train the language model to be able to figure out what those masked words are based on the context. In our use case, as it has been done in previous works, we reinterpret these language models. Instead of sentences, we use mouse strings, and instead of words, we will have the various characters that represent the atoms and the bonds in the molecule. In the natural language processing case, other than learning to predict the masked tokens, there are various tasks you can train BERT on: sentiment analysis, question answering, or predicting whether 2 sentences follow each other or not. Instead of these tasks, we train the model to predict physicochemical properties, and inspired by the next sentence prediction task, we predict whether a pair of input smiles represent the same molecule or not. After training, we use these models to represent these molecules, and we test this representation by the industry standard benchmark, the RDKit benchmarking platform. Based on the results of this benchmark, we explore various questions. Which tasks are beneficial for learning useful representations? How does our method compare to other state-of-the-art descriptors? We also conduct several ablation studies, trying to answer questions such as whether it's useful to permute the input smiles, or it's better to stick to the canonical form. Also, which physicochemical properties are the most useful? We also investigate how much data is necessary to learn these representations. If you also find these questions interesting, please come to our poster to discuss our work. Thank you.
Hi, I'm Wen Hao. The title of my poster is "Can we synthesize molecules proposed by generative models?" We know AI is accelerating the chemical discovery process by learning chemical intuitions and proposing structures with high scores in some computational oracles like log-P or QED. But those algorithms only explore a digital chemical space. For example, all structures that are valid according to RDKit. And there is a gap between the digital chemical space and the physical world in which we would synthesize the molecule eventually. To highlight this problem, we quantified synthesizability using a data-driven retrosynthesis planning program called ASCOS. We investigated the common databases and the current state-of-the-art generative algorithms. We proposed and tested several approaches to synthesizable molecular generation. Apart from my poster, you can find more information about this topic in my paper, my code, and on 1 hour video on YouTube. Feel free to contact me or Connor if you have any question or are interested in what we are doing. Thank you.
Hello, I'm Tom Hadfield, PhD student in the Oxford Protein Informatics group, and I've been working on a fragment elaboration model for fragment-based drug discovery. Elaboration is time-consuming and expensive, and the kind of elaborations you'd like to make vary drastically depending on the pocket that you're working with. And our model takes this into account by explicitly incorporating structural information into the training process, which is something that no other available model does. And our method works by first training a universal fragment elaboration model, which can take any fragment as input and adds atoms whilst keeping the original fragment fixed. And then we use reinforcement learning to fine-tune the universal model for a specific use case. And the reinforcement learning algorithm incentivizes the model to make elaborations that match a pharmacophoric profile. The profile can be extracted by looking at the binding pocket. So this method would still work even if there were no currently known actives against the target. And we compared the performance of our RL enhanced model to the universal model and a recently published elaboration model called reInvent. And we tested it on examples from the Malhotra set, which contained paired ligands found in the PDB, where the smaller ligand is a substructure of the larger ligand. And we made elaborations to the smaller ligand with the aim of constructing molecules that were 3D similar to the larger one. And we assessed the performance of each model by the number of distinct elaborations which are above a similarity score threshold, and found that our RL enhanced model outperformed the other two models. And thank you very much for listening. If you'd like to find out more about the model, please see my poster number 15. And please feel free to contact me at the addresses listed on the slide, or I'd be very happy to chat at one of the sessions during the symposium. Thank you.
Chemoenzymatic synthesis combines enzymatic and organic reactions to take advantage of the selectivity of enzymes without sacrificing the versatility of organic chemistry. While there are many tools that predict either purely organic or purely biochemical pathways, currently there are no computational tools that are tailored to discovering pathways that combine the two. Building off the ASCOS retrosynthesis platform, we developed new tools that are able to automatically suggest promising chemoenzymatic syntheses of input molecules. First, we trained a new one-step template-based retrosynthesis model that scores the possible enzymatic reactions to make a target molecule. We used this new enzymatic model alongside the previously trained ASCOS one-step model in a pathway search algorithm that automatically discovers synthesis plans that use enzymatic and organic steps. The search algorithm starts from the input target molecule and recursively considers precursors until the target molecule is connected to viable starting materials. The algorithm uses the scores from both the enzymatic one-step model and the ASCOS organic one-step model to guide the search and limit the number of precursors considered at each step to avoid an exponential growth of the search tree. Our new strategy was able to automatically generate promising synthetic pathways to a chiral biaryl alcohol and to S-stylopene. The benefit of our approach is demonstrated by the fact that these pathways are more stereoselective and run under milder conditions than comparable reactions suggested by a purely organic synthesis planner. In the future, the relative likelihood that our pathway planner will suggest an enzymatic step or an organic step can be tuned by modifying the relative magnitude of the outputs from the corresponding one-step models. We plan to apply this new chemoenzymatic pathway planner to find synthetic routes to molecules that are difficult to access by pure enzymatic or organic synthesis.
Hi, I'm Greg McCarra from Campass. Campass has developed an integrated end-to-end AI-assisted lead discovery platform that can meaningfully shorten development time and significantly decrease preclinical cost. This platform allows us to re-engineer the traditional hit-to-candidate process, and instead of hit-to-lead, have an initial phase of lead expansion and data generation. The number of hit series is expanded to several tens, sometimes even 40+ different chemical classes, with experimental data generation for each series. These include binding, ADMET, and other necessary data types for models we are planning to use throughout the program. Thanks to our synthesis-based design process, the actual synthesis and experiments can be done in as little as 5-6 months for all series in this phase. With all this information and a variety of potent ligand types in hand, the lead optimization becomes a more streamlined process with many chemical classes carried through the process. As opposed to generative design with deep networks, ChemPass's unique small molecule design platform uses artificial intelligence for forward synthesis, resulting in novel lead analogs, and importantly, they all come with valuable practical synthetic feasibility data. The platform has multiple design technologies that have been validated in many projects with partners. These include specific modules for scaffold hopping or sidechain design in SynSpace, as well as general powerful technique called derivatization design. The latter can create both closure analogs and new scaffolds in one design run, or it will only produce either depending on the user settings applied. In our poster, we introduced this highly automated technique and compared its results to a recently disclosed DDR dataset obtained using generative design. Please visit poster 21 for more details during the conference or contact us at any time after.
Hi guys, today I'm going to talk about my work on enhancing molecular fingerprints using neural networks. Molecular fingerprints are used in similarity search to identify new molecules with desired properties. The issue is that fingerprints are static in that they do not change across different chemical domains or tasks. However, task or domain-specific information can be crucial for a successful similarity search. Our idea was to use neural networks to make fingerprints more adaptable to specific tasks. The basic idea is to train neural networks for target prediction and use the activations of the last hidden layer as a new fingerprint. We hoped that the network would combine structural information on the molecule and implicit knowledge on the task as well. This should elevate the performance of the neural fingerprint compared to traditional ones. To generate the neural fingerprints, we used two different architectures. One was a graph convolution network and the second was a multi-layer perceptron using a traditional fingerprint as input. The models were trained on a large kinesis dataset, and each architecture was trained for two different prediction tasks. One was to predict a general kinase likeness, and the second was a multitask classification in which the correct kinase targets for each compound had to be identified. Here I show the 1% enrichment factor for each of the fingerprints. The enrichment measures how many actives are in the top 1% relative to the complete dataset. The generic models failed to provide an enrichment better than that of the ECFP4. However, all multitask models outperform the ECFP, most noticeably the MLP, with an enrichment twice as large as any other fingerprint. This is true even when we remove kinase targets from the training set. These results show that neural networks are capable of improving fingerprints and even work when specific targets were not included in the training. Surprising was that the GCN performed much worse in similarity search. We believe that is due to the low expressive power that many current graph neural networks.
Thank you very much for giving us the opportunity of presenting our work here on non-additivity in public and in-house data and its influence on machine learning performance. Most of the work I'm showing here has been done by the master student Diego Gashvili. Most of the methods we are currently using in computer-aided drug design are based on the assumptions of similarity, as in compounds with similar structure have similar activities, as well as on linearity and additivity in the chemical space. Herein, this is a precondition for extrapolation and prediction of unknown data from known data. Non-additivity is calculated using so-called matched molecular squares. Herein we have four compounds that are connected by two distinct chemical reactions. The non-additivity is then calculated using the delta in their activities. Herein we used the non-additivity analysis for public Campbell data and in-house AstraZeneca data. Thus we could show that 9.3% of in-house and 5.1% of public data shows significant non-additivity. Thus, we were wondering, how does the non-additivity influence the performance of machine learning? We have used therefore a couple of Campbell data sets, and we could show that data with non-additivity cannot be accurately predicted, as you can see here in the right plot, where we have two different test sets, one with only additive data, which is well predicted, and one with non-additivity, which is not predicted well at all. Also, the model performance does not increase when we add non-additivity data to the training set. So overall, non-additivity plays a significant role, and it has to be considered on a more regular basis than it is currently done in computer-aided drug design. If you want to know more about it, please come and have a look at my poster. It's poster number 27. Feel free to send me an email and I'm happy to set up a virtual meeting. Thank you very much.
Welcome to this 2-minute talk on the classification of chemical reactions through natural language processing inspired fingerprinting by me, Daniel Probst, Philipp Schwaller and Professor Jean-Louis Raymond of the University of Bern and IBM Research. The fingerprint of a molecule is usually generated by first splitting the molecule into parts, such as substructures or paths, and then hashing those parts based on their properties into a binary array. We recently introduced the MHFP fingerprint, which is based on natural language processing. We don't treat the parts of the molecule as substructures, but solely as strings, which are then directly hashed using the min-hash technique. We now applied the same technique to reactions, where we first divide reactions into reactants and reagents, as well as products. Both sides are then fragmented into sets of overlapping smile strings, so-called shinglings. The symmetric difference of the two sets is then min-hashed into a binary reaction fingerprint. In a reaction classification recovery study based on the NextMove software Pistachio dataset, the new reaction fingerprint outperformed a state-of-the-art traditional fingerprint and came within 10% of the performance of a deep learning-based fingerprint, which was trained on proprietary data. In a yield prediction study on Buchwald-Hartwig aminations, a multi-layer perceptron trained on the reaction fingerprint data performed approximately as well as a deep learning-based method and outperformed a DFT-based method. Thank you for listening, and many thanks to Philipp Schwaller and Professor Jean-Louis Raymond.
In this video, I'm presenting Reaction Mapper, unsupervised attention-guided atom mapping. Chemical reactions describe how precursor molecules react together and transform into products. Using smiles, a text-based molecule representation, chemical reactions can be represented as text and tokenized atom by atom. The SMICE representation makes it possible to apply transformer models to chemical reactions. Transformers are made of stacks of self-attention layers, and every layer has multiple heads to learn functions to attend their input tokens. We trained transformers on millions of unlabeled reaction SMILEs. For the training, we used a mask language modeling task, where input tokens are randomly masked and then predicted by the model given the context. Once we had a trained model, we visually inspected the attention weights. The mind-blowing discovery was that all the models had captured how atoms rearrange during a reaction. This challenging task is also called atom mapping. We used the atom rearrangement signal to build Reaction Mapper. On a test set of 49,000 chemical reactions, we found that Reaction Mapper mapped more than 99% correctly. Sometimes even better than the ground truth. The atom maps are not only of high quality, but can also be generated much faster than previous tools. Atom mapping is crucial as it allows to automatically extract reaction centers, bond changes, and reaction rules, the grammar of chemical reactions. Therefore, atom mapping affects many downstream applications. We discovered that transformers trained self-supervised on chemical reactions capture their hidden grammar and developed Reaction Mapper, which efficiently produces high-quality atom maps. For more information and the demo, visit reactionmapper.ai.
My name is Alain Vaucher, and I am a research scientist at IBM Research in Zurich, Switzerland. Recently, we have been looking into learning how to do chemical reactions from data. The thought that started this project was that the chemical literature contains not only millions of chemical reactions as given by the structures of the reactants and products, but also millions of experimental procedures detailing how the reactions were actually executed in the lab. With this in mind, we have, in principle, enough data to automatize the design and the synthesis of chemical compounds with the help of robotics and AI. This pipeline of going from a target compound to the automatic synthesis in the lab can be divided in 3 consecutive steps as represented by the box on the top of this slide. The first task on the left is to determine an adequate retrosynthesis for the compound of interest. While many approaches exist for this task, at IBM we have been looking into language-based models that iteratively determine potential precursors by translating from the language of chemical products to the language of chemical precursors. The second task in the middle is addressed by an AI model that determines, for each reaction step, a precise sequence of synthesis actions to perform in the lab. These actions are expressed in terms of additions, stirring, concentration, extraction, and so on. To make this possible, we first trained another AI model to extract synthesis actions from text. The third step on the right is the automated execution of the synthesis on the robotic system. In our setup, a user can launch the synthesis remotely from the web browser, potentially thousands of kilometers away. This concludes this lightning talk. Don't hesitate to check my poster or contact me for more information.
In poster 43, we'll give a bit of information and background on Avatec's eApps platform. eApps is an integrated web-based computational medicinal chemistry platform designed in-house to collect a number of powerful data processing and analysis tools in one place, with a common interface for improved data sharing. It comprises of a web page front end that links to the HPC systems running the applications, third-party or otherwise, meaning that powerful jobs can be initiated from even the lowest spec workstations. Being cloud-based, eApps provides users with space to work and collaborate within projects through assigned workspaces. Once you've loaded data in, users can instantly process the structural and chemical information in a spreadsheet view, as well as view styles and plots to assist in mapping the data within chemical space. Reporting analysis can be performed directly within the platform should you need it, and again, that can be shared externally. At present, eApps provides the input and visualization interface for our protein ligand docking system and machine learning modeling, both user-made models and pre-made models. If you want to do multi-parameter optimization, that's here as well, again combining common functions such as ligand efficiency, central nervous system scores and the like, with the tools to build your own, as well as support for Pareto front operations and desirability calculations. AI-assisted structure generation takes the form of a reaction-based structure design tool, fully configurable using data pulled out of our own ELN, literature, and US patent reaction data. Pick a set of reactions or add your own to be applied in silico to your starter structure, with common reagents if needed. This standard AI setup will do real-time recommendation of reaction classes too from the structure that you input. This is as well as matched molecular pair processing from DMPK, Chembl, and internal knowledge bases, and implementation of the SLURP structure interpolation tool all built in. In short, there's a lot here for those trying to take the drudgery out of data analysis and prediction. So by all means, take a look and see what you think.
Hello everybody, this is Yuanqing Wang. I'm a PhD candidate in John Codera Lab in Memorial Sloan Kettering Cancer Center here in New York City. In this paper with Michael, Man from UPenn, John, and Theo from Facebook, we asked the question of what it would take to entirely replace the human decision-making element within a drug discovery campaign. The preclinical stage of drug discovery, which typically takes many years and hundreds of millions of dollars, is done in an iterative manner, shown in the left. An expert team of medicinal chemists choose compounds to purchase or synthesize, conduct assays on those compounds, update their belief of the system using the gathered data, and accordingly acquire the next batch of candidates. On the left-hand side, we show how our proposed Bayesian optimization loop works, where decision-making is done based on a model which predicts the relationship between the graph structure and the biological activity of compounds. In this paper, this model is chosen to be a combination of graph nets and a Gaussian process regression. As a proof of concept, we use the data from an open source project, COVID Moonshot, which searches for potent inhibitors of MEN protease of SARS-CoV-2, the virus responsible for COVID-19 pandemic and the reason why we're not together in Cambridge today. This project is ongoing as we speak. The records of how human experts prioritize compounds are published and uploaded every week. We use the timestamp to characterize the so-called human expert policy, which our Bayesian optimization competes against. In one of our experiments to illustrate the utility of the model after each round of acquisition, we trained a supervised learning model and plot a maximum value of some acquisition function over the rest of the data. Note that for both humans and for BO, best or near best candidates are always discovered within the first 2 rounds. So an ideal policy would be pessimistic very quickly from that point on and predict both these acquisition functions to be near 0. Anything beyond that can be called over-optimistic. We show that our acquisition policy is less so, which we believe could say that the BO loop gathers information about the best candidate within the pool faster. Thank you.